So now we are going to look at elimination. Suppose there are two equations given to us in some variable. So the variable is theta and a and b are real coefficients. So we would like to eliminate theta from these two given equations. So if we were to add these two equations, so, this is not going to work. So what I have in mind is, suppose a plus b sine square theta plus cos square theta is equal to c. A sine square theta a sine square theta plus b cos square theta and b sine square theta so to start with, suppose these two equations are given and a, b and c, d are real numbers and they're constants and theta is a variable. So the meaning of elimination is to get a relation between the coefficients so that the theta doesn't appear in the final relation, which will be called eliminant, and the process of getting an eliminant is called elimination. So if we were to add these two equations, sine square theta a plus b and we know sine square theta plus cos square theta is equal to 1 for all theta. This is the eliminant, since sine square theta plus cos square theta is equal to 1 for all theta. So there is another place where we can use this process of elimination. For example, an equation is two equations are given. So first thing to note is there is always a zero solution, that is x is equal to 0 and y is equal to 0 will always be a solution. But if we are to insist that there are non-zero solutions to this, then we can, let's just say, solve the first equation and get since y is not 0, and from the second So from these two we can eliminate, we can equate these two to get A12 A21 minus A22 A11 equal to 0, which is same as saying A12 A11 A22 A12 A21. So this will be the eliminant of these two equations. There is another way also in which we can arrive at this eliminant. So these were the equations. This can be written as product of two matrices. This is a 2 by 2 matrix, this is a 2 by 1 matrix. The product will be A11x plus A12y, which is the first equation, equal to 0, and then A21x plus A22y equal to 0. That's the second equation. If this matrix, we can write like this: Ax is equal to 0, where x is the variable matrix and A is the coefficient matrix. If this matrix A were to be invertible, then we can pre-multiply by A inverse, and the only solution will be x equal to 0. So if there are going to be non-zero solutions, we have to say that A is not invertible. And if A is not, it's a theorem that it can be proved that if A is not invertible, then determinant of A must be equal to 0. That amounts to the same thing, the relation, the eliminant which we obtained in the previous method. So this can be done for 3 variables also. 3 variables, 3 equations, or 4 variables, 4 equations. That's the next 2 articles in the book. We are following SL Loney's coordinate geometry.